This presentation is part of the 14th Algorithmic Number Theory Symposium held from June 29th to July 4th, 2020. I am Nils Bruin and I'm reporting on joint work with Daniel Lewis. Part of this work was executed as part of Daniel's master's thesis project at Simon Fraser University under my supervision. I'll start out with a quick overview of our main contributions and results, and then spend the rest of the talk on motivation and details. Our main contribution is a practical method to decide if certain smooth-plane quartics have rational points. Certain here means all 28 bitangents of the smooth-plane quartic are rational. We generate plenty of examples using some classical algebraic geometry concerning del Pezzo surfaces of degree 2, and we find that our method is surprisingly successful. On all the 150,000 test cases that we tried, we were successful in deciding whether the curve has a rational point or not. We do expect that failures occur eventually, but we haven't just not been able to find any cases where we were not able to decide the existence of rational points. We found some bonus material as well. Our computations allow us in certain cases to get some information on Mordell groups of the Jacobians of these curves, in particular about their two Selmer groups, and we compare our findings with the Poon and Rains heuristics about how the sizes of such groups should be distributed. We find that they're well matched provided one shifts the distributions in a particular way. This shift is possibly justified by observing that Jacobians very often have an everywhere locally trivial torsor representing pick 1. Okay, we'll now go to a little bit of the background material. A motivating question in arithmetic geometry is the decision problem of whether or not a variety has a rational point or not. In particular, for projective plane curves, which are curves given by a homogeneous degree D equation in 3 variables in the projective plane, a rational point would be a projective point for which the coordinates can be given in the base field K. And we say that a curve is solvable if it has a rational point. Otherwise, we'll call it insolvable. It's easy to give examples of either. For instance, if one takes the equation for the standard circle, x squared plus y squared minus z squared, and it's easy to see that there are rational solutions to this. On the other hand, if we take x squared plus y squared plus z squared is 0, then there are no non-zero solutions, and so there are no projective points on such on the corresponding curve. And similarly, if one takes x squared plus y squared minus 3 times z squared, there are no rational points there either. In order to show that a curve does have a rational point, there's an easy, although perhaps inefficient approach. One can simply enumerate the rational points over a number field. A number field is enumerable after all, and one will eventually stumble on a rational point if it exists. To prove insolvability, one might be able to prove that, for instance, there are no real or p-adic points on the curve, and then because Q is a subfield of these larger complete fields, it follows that there aren't rational points either. This last remark is one example of an obstruction. We say that a curve over a number field has a local obstruction to having rational points if for some completion of the number field we can show that there are no rational points. Deciding if a curve has rational points over a completion of a number field is actually something that is a decidable problem. There are relatively efficient algorithms for doing so. Local obstructions are insufficient in general, though. For curves of degree at least 3, one can give examples where we know that there are no rational points and yet there are no local obstructions either. Selmer gave a famous example of a cubic equation like this. In those cases, the theorem of Chevalley-Wey might help a little bit. A slight translation of that theorem gives us that if we have an unramified cover of our curve C, then one can determine a finite collection of twists of this cover. That is a collection of covers that are in some way rather similar to our original cover, such that the rational points on C are covered by the images of the rational points on the covers. This leads to the definition of the Selmer set, where we take the subset of covers that have points everywhere locally. If the Selmer set is empty, then none of the covers can have rational points, and hence, by Chevalier, there aren't any rational points on the curve either. The interesting observation is that one can actually use this obstruction to prove that there are no rational points, even if the curve does have points everywhere locally. An example of this is the following. If we consider the following genus 1 curve given by the affine model here, the form y squared equals a quartic in X, where the quartic factors in two quadratic factors, we can construct a cover in the following way. We set each of the quadratic factors equal to almost a square in such a way that their product gives a proper square. With these covers, it's also clear that if there were a rational point on C, one could take its x-coordinate and simply solve for an appropriate psi. The fact that it's the x-coordinate of a rational point on C allows us to solve the rest of the equations as well. Careful consideration shows us that these d psi can only have rational points if we take psi to be either 1 or 2. And for each of those values, in fact, we can show that there's still a local obstruction anyway. So the Selmer set of this genus 1 curve is empty, but the curve itself actually does have points everywhere locally. This idea is applicable to a lot of curves. One just needs a way of generating appropriate unramified covers. One cover that is suitable for such purposes is a 2 cover. Given a curve C of genus G, the 2 cover would be a cover for which the automorphism group is an elementary 2 group of rank 2G, where G is the genus of the curve C. One can prove that such 2 covers always exist, certainly if the curve has a rational point. And one can then use Chevalier to compute an appropriate 2 Selmer set of the curve C. This has been studied for hyperelliptic curves in quite a bit of detail. A hyperelliptic curve here is a curve that admits a model of the form y squared equals f of x, where the degree of f is 2g plus 2. It's known that local solvability is something that applies to a lot of hyperelliptic curves. And in joint work with Stoll, we provided a relatively efficient methods for computing the 2 Selmer set of a hyperelliptic curve. A particularly easy case there would be if the curve had all its Weierstrass points rational, that's to say, if the polynomial f factors into linear factors. From the point of view of deciding if there are rational points, this is rather uninteresting, because in that case there are plenty of rational points on our curve. So there's little left to decide. These methods have been used for average results as well, though. Bargevag, Gross, and Wang in 2017 proved that most hyperelliptic curves have an empty 2 Selmer set. So combined with the local solvability result, this really gives you that violations of the local to global principle are ample for hyperelliptic curves. Okay, it does leave a question: how do these results generalize to non-hyperelliptic curves? We try to make a step in that direction here. One reason to be interested in non-hyperelliptic curves is because, well, most curves are non-hyperelliptic, and hyperelliptic curves are special in the sense that they have this hyperelliptic involution on them. They have a non-trivial automorphism group, which is a rather atypical thing for curves in general to have. So the easiest case to consider for non-hyperelliptic curves is in genus 3, where the non-hyperelliptic ones admit a smooth plane quartic model. The analog of a Weierstrass point in this case is played by a bitangent line. The equation in general is of degree 4, so a line would cut the curve in 4 points, but these points can coalesce into 2 points with multiplicity 2, in which case you'd have a line that's tangent to the curve in 2 points. The interesting thing is that if we take the linear equations that define 2 bitangents and take their quotient, we get a function on the curve that has poles and zeros of even multiplicities. That means that adjoining its square root gives an unramified cover of our curve C. In general, there are 28 bitangents on a smooth plane quartic, so that gives a possibility of 378 quotients of linear equations defining bitangents. Adjoining all the square roots yields an unramified cover of degree 2 to the power 6. There are plenty of relations between these. So that's an avenue towards getting a 2 cover. And in particular, if the bitangents are defined over the base field, then this gives a fairly straightforward recipe for writing down equations for the 2 covers of a smooth plane quartic, and that gives us an avenue to computing the 2 Selmer sets of such curves. In order to generate examples where we can apply these methods, we employ some classical algebraic geometry of degree 2 Del Pezzo surfaces. These surfaces have 2 geometric descriptions. One is as a blow-up of P2 in 7 points in general position, and the other is as a double cover branched over a smooth plane quartic. It's the second description that's of interest to us because that gives us access to the smooth plane quartic. But there's an interesting relation here, and that is that if one takes the 7 points that one blows up to be defined over the base field, then the bitangents of our curve C will be defined over that same extension. If we put coordinates on this, we can choose the first 4 points to be the standard simplex, and that leaves us 3 more points to choose, meaning that we get 6 parameters in total, which matches the dimension of the moduli space of genus 3 curves. This configuration already leads to an amusing proposition. Over F3, F5, and F7, there are simply no such configurations. The projective planes over these fields have too few rational points to find 7 in general position. Over F11, one can find points in these configurations, but it turns out that they all lead to isomorphic curves, and it turns out that the one curve that has all its bitangents defined over F11 is pointless over F11. We can conclude from this already that any example of a curve with rational bitangents over Q that's everywhere locally solvable is going to have bad reduction at 3, 5, 7, and 11. As an explicit example, we choose the parameter values listed here, leading to a relatively horrible equation for a plane quartic. We can compute the discriminant of this. The divisors of this are primes of bad reduction. And indeed, one can see that 3, 5, 7, and 11 occur here. And this curve is indeed everywhere locally solvable. The initial F2 vector space containing the 2 Selmer set of this curve is of dimension 72. This 72 arises as 1 plus the number of primes times 6. And that is, it arises as the rank of some S-unit group. The problem here is that 2 to the power 72 is way too large to enumerate, so we need some extra work, but with some linear algebra and extra computations, one can reduce this dimension quickly to just 9, and that is an enumerable set from a practical point of view, and it allows us to just prove that the 2 Selmer set is empty by basically enumerating each of those curves and then testing that they have a local obstruction to having rational points, and as it turns out, just the obstructions at 2, 3, and 5 here are already enough to conclude that our curve has no rational points. This is only one example, but in fact we tested this method systematically on a wide range of examples. We had one test batch where we systematically enumerated all possible configurations with coefficients between -6 and 6. That gave us roughly 81,000 test cases. There are probably some isomorphic examples between them, but we do find 33,000 distinct discriminant values, so we don't have too many multiple representatives of the same isomorphism classes there. We also generated our parameters by choosing them randomly from the interval -40 to 40. That gave us 70,000 curves, all with distinct discriminant values. Here we tabulate our findings. So a relatively small number of curves ends up having a local obstruction. And interestingly enough, we only find local obstructions at 2 and 11, and only when the curve has good reduction there. The 2-Selmer set in all these cases is empty in a lot more cases, and certainly the first column is contained in the second one. Whenever these 2-Selmer sets end up being non-empty, we were able to find either that one of the contact points of one of the bitangents is rational, or that there is some other rational point on the curve somewhere. So together this allowed us to actually decide for all these curves whether there's a rational point on them or not. As a bonus, we were also able to derive some information on the 2-Selmer groups of their Jacobians. We've plotted the distribution of the different dimensions as F2 vector spaces of these groups, and we compared them to the Poonen-Rains heuristic, which predicts that the distribution one should get out of these ranks is as basically, well, some base value C plus an excess size that for which they conjecture a certain distribution. And we find, especially in the row B here, a fairly good match with those values, but it's a little surprising what a shift we need to take there. One certainly expects that C needs to be at least 6, because the rationality of the bitangents forces the 2 torsion on the Jacobian to be entirely rational, and that already contributes a subspace of dimension 6 to the 2-Selmer group. But we find an extra shift by 1. As you can see here in the B column, the ranks are in fact at least 7. The observation that might explain this is that here these curves C basically have points everywhere locally almost all the time, so the pick ones have points everywhere locally. That means that the representing scheme provides an everywhere locally trivial torsor under the Jacobian, and that is an indication, and that contributes something to the 2-Selmer group, and it's an indication that Jacobians might actually have some different arithmetic behavior from that for general abelian varieties, because the existence of such torsors is actually something one expects for Jacobians and not for general abelian varieties. Thank you for your attention.